So we've been looking at game theory for two-person zero-sum games that had a stable solution. That is, the payoff matrix had a saddle point, and there was always a best solution we could get by using the minimax method. But that's not always the case, and the nice example that's discussed at some length in the book is the following. Suppose we have a two-player game, and for player one, we have three strategies. For player two, we have three strategies. And the payoff matrix is as follows: 0, -2, 2, 5, 4, -3, and 2, 3, -4. So let's look at the minimum on each row, each strategy for player one. Here the minimum is -2. Here the minimum is -3. And here the minimum is -4. So this is the smallest number in the first row, but it's not the maximum in the column. This is the smallest number in the second row, but it's not the maximum in the column. This is the smallest number in the third row, but it's not the maximum in this column. So there's no saddle point. For this payoff matrix. Which is the smallest of these numbers? It's 2. This is the minimum, this is the maximin. This is the maximum. Sorry, what is the largest of these numbers? It's -2. This is the maximin. It's the maximum of the minimum. So if player one chooses strategy 1, she loses at most 2. Strategy 2 loses at most 3. Strategy 4 loses at most 4. So the best you can do is to lose at most 2 by choosing strategy 1. What about player 2? Player 2 wants to minimize her loss. You look at the maximum in each column, because this is the payoff to player 1. So the maximum is the most player 1 gets, which means the worst that player 2 can lose. Here the maximum is 5, here it's 4, and here it's 2. And the smallest of these numbers, let's call it, it is called the minimax. That's 2. So player 1 can lose at most 2 by choosing strategy 1. Player 2, if player 2 chooses strategy 3, in fact, what happens is player 1 doesn't lose 2. Player 1 gets 2. That's nice for player 1, but player 2 doesn't like that. So player 2 can say the following to herself: well, I know that player 1 is going to choose strategy 1. In that case, I'll choose strategy 2, because in that case, I'll win $2. So that's what player 2 will do. But player 1 can reason the same way. Player 1 says, if player 2 is going to choose strategy 2, instead of losing $2, instead, I should pick strategy 2, and then I'll win $4. Player 2 says, well, okay, now player 1 is going to play strategy 2. I can actually win $3 if I choose my strategy 3. -3 is a $3 loss to player 1, so a $3 win for player 2. But then player 1 says, wait a minute, if I know player 2 is choosing strategy 2, I'll pick strategy 1 and win $2. And they keep reasoning like this, and they go into this loop, and there's no strategy that works for either of them. It's like an unresolved game. There's no saddle point and there's no strategy for either player to minimize the loss. If they're acting rationally and trying to make as much gain as possible. So this model in which each player just chooses a strategy and that's it, these are called pure strategies. Or to be precise, the pure strategies for each player are 1, 2, or 3. You choose one, that's it. And this doesn't give us a way to solve this game or to come up with a solution that gives an optimal strategy for both players. They keep going around in this infinite loop. They never settle on anything. So instead, what we're going to do is assign probabilities to each player to choose a strategy. So let me just remind you about the very simplest fact about probability. So in probability, suppose there are M, in this case, M is 3, there are 3 strategies for each player. Suppose there are M choices and we choose I, the ith choice. I is from 1 up to M. With the probability we'll call X of I. So X of I, the probability of choosing I, is a number between 0 and 1, and the sum of all the probabilities for all the choices has to add up to 1. So for example, if you're flipping a coin, there are 2 choices or 2 outcomes that are possible. And if it's a fair coin, the probability of getting a head is a half, the probability of getting a tail is a half. A half is a non-negative number between 0 and 1, and a half plus a half is 1. That's the simplest, most classical example of a probability. So let me just describe the general situation, and then we'll specialize it to the small examples that we're going to consider. So suppose we have the following payoff matrix. So let's say for player 1, there are M strategies. And for player 2, doesn't have to be the same number. Let's say there are N strategies. So N strategies for player 2. And let's say we describe the payoff is the following. So if player 1 picks strategy 1 and player 2 picks strategy 1, the payoff is P11. If player 1 picks strategy 1 and player 2 picks strategy 2, the payoff is P12, P13 up to P1N, and so forth. We just write Pij is the payoff if player 1 chooses strategy 1, chooses strategy I, and player 2 chooses strategy J. So this is really just a matrix with M rows and N columns, and the ijth coordinate is Pij. This is the payoff. And suppose each player, instead of choosing a strategy and playing it, is going to do something analogous to flipping a coin or rolling a roulette wheel and choosing a strategy with a given probability. So xi is the probability that player one chooses strategy I. And this I goes from 1 to m. So x1, x2, x3 down to xm. These are the probabilities that a given strategy is chosen. And for j, between 1 and n, y sub j is the probability that player 2 chooses strategy j. So what is the expected payoff? So for every I from 1 up to m and every j from 1 up to n, you choose, player 1 chooses strategy I and player 2 chooses strategy j with payoff pij with probability xi times yj. So in probability theory, you don't have to know any probability theory for this, but this is just the standard definition of the expectation or the expected payoff of this game. Now, what do we do? How do we actually apply this in practice? So what is called the minimax theorem says that if we can figure out a way to calculate a best strategy using probabilities for each player, they will give you the same result. You have a stable solution. And we're going to consider the special case, the simplest case, when at least one player has only 2 strategies to choose from. So let's look at the example we started with. In the start, each player has 3 strategies. The payoff table was 0, minus 2, 2, 5, 4, minus 3, and 2, 3, minus 4. Now, if we look at this table, we see that strategy 3 dominates. Oops, that's not right. Is there one strategy dominating another? Yes. Strategy 2 dominates strategy 3. If you look at strategy 2 and strategy 3, 5 is bigger than 2, 4 is bigger than 3, minus 3 is minus 4. So for player 1, strategy 2 dominates strategy 3. So we can cross out strategy 3. We're never going to choose that. And now player 1 has really just 2 strategies to choose from. So suppose we let, so this is the strategy. Suppose I write down the probability, x1 and x2. So x1 is the probability that player 1 chooses strategy 1. And x2 is the probability that player 1 chooses strategy 2. And the sum of the probabilities, x1 plus x2, is 1. So that says immediately that once you know x1, x2 is always 1 minus x1. Okay. So let's try and figure out what is the best thing for player 1 to do. So if player 2 chooses strategy 1 for player 2, that's this first column, then what is the result for player 1? What is the payoff? Then for player 1, the payoff is strategy 1 is chosen with probability x1. So it's x1 times the payoff in that case, which is 0. Or if player 1 chooses strategy 2, that happens with probability x2, then the payoff is 5. So this is x1 is 0. This is just 5x2. And x2 is 1 minus x1. So this is 5 minus 5x1. x1, of course, is always between 0 and 1 because it's a probability. And if player 2 chooses strategy 1, the payoff to player, the expected payoff to player 1 is 5 minus 5x1. If player 2 chooses strategy 2, then we're looking just at the second column. The payoff to player 1 is x1 times minus 2 plus 4 plus x2 times 4. That's minus 2x1 plus 4x2, which is 1 minus x1. So that's equal to 4 minus 6x1. And if player 2 chooses strategy 3, that's this third column, then the payoff to player 1 is 2x1 minus 3x2. That's 2x1 minus 3. Again, x2 is 1 minus x1. This is equal to minus 3 plus 5x1. So we can actually make a graph of this. So x1 goes from 0 to 1, and 5 minus 5x1, as x1 goes from 0 to 1, this is a line with y-intercept 5 and slope minus 5. So that's this line. So this is the line 5 minus 5x1. 4 minus 6x1, that's a line with y-intercept 4 and slope minus 6. So when x1 is 1, this is minus 2. This is the line 4 minus 6x1. And the line 3 plus 5x1, that has slope 3 and Oops. This is a -3. This has, sorry, it has y-intercept -3 and slope 5. So when x1 is 1, this is 2. It's this line. This is -3 plus 5x1. And what do these lines represent? This is the expected payoff to player 1 choosing x1 is the probability for strategy 1 and x2 is the probability for strategy 2. So depending on what player 2 does, these are the payoffs, the expected payoffs to player 1. So, for example, if you look at this line, -3 plus 5x1, this is where player 2 chooses strategy 3. Depending on what player 1 does, what probability he chooses his strategy with, x1, he's losing money. Now, if x1 is bigger than whatever this number is, he's winning money, and he wins more and more and more. So -3, this is when player 2 chooses strategy 3. This is when player 2 chooses strategy 1. This is when player 2 chooses strategy 2. So this is how much player 1 can be expected to win. He could lose or he could win. If player 2 chooses strategy 2, player 1 will win. But if he chooses x1 too large, then he starts to lose. And if player 2 chooses strategy 1, player 1's always going to do well, but do better. But you don't know what strategy player 2 is going to choose. So player 1 wants to minimize his risk. He wants to make sure, he wants to pick a strategy where he minimizes how much he can lose. And for any given value of x1, these 3 points are how much player 1 wins. This is the worst he can do. This is the worst he can do. Where do you make this worst as big as possible? That is, you want to make sure you lose, that you can't lose too much. So this is how much you can lose. This is the worst you can do for each strategy. And that's best when you exactly choose x1 here, which is the smallest point. So for each of these lines, you look at the minimum, you get this V-shaped curve. For this strategy, the minimum is as large as possible. So what this means is that the best or the optimum strategy for player 1 is to choose x1 such that it's at the intersection of these 2 lines. This line is 4 minus 6x1. This line is -3 plus 5x1, and where they intersect, that's this value of x1. This is the same as 11x1 equals 7. So x1 equals 7 over 11. That means, and if x1 is 7 over 11, x2, which is 1 minus x1, is 1 minus 7 over 11, is 4 over 11. So what this says is that player one, who wants to minimize the most he can lose, does best by choosing strategy one with probability 7/11 and strategy two with probability 4/11. And in that case, what is his expected playoff? Expected payoff to player one is you just plug 4/11 into either one of these two expressions. 4 minus 6 times 4/11 is 4 minus 24/11. Let's see, something is not right with my arithmetic. Oh, 7/11. That's better. 4 minus 42/11, which is 44/11 minus 42/11 is 2/11. So the optimum strategy for player one is to choose the probability of picking strategy one with 7/11, strategy two with 4/11, and the expectation, that is, if he does this, this is probability. This means that if you were to do this strategy over and over again many times, your average earnings will be plus 2/11. So this is an example of what is called the graphical method to solve a game theory problem when at least one player has two solutions exactly to choose from. When there are two solutions, you get straight lines and you can draw a graph. So that's the graphical method. And I will demonstrate this by doing one of the homework problems. So let me pause for a second and turn to the homework problem. So let's look at problem 15.4.3. So we have a game with the following payoff table. There are two strategies for player one, two strategies for player two. And the payoff is 3 minus 2 minus 1, 2. So first of all, we notice that there's no dominating strategy for either player. So if you compare the first and the second rows, 3 is bigger than minus 1, but minus 2 is smaller than 2. And if you compare the first and second columns, 3 is bigger than minus 2, but minus 1 is smaller than 2. So there's no dominating strategy. There's also no saddle point, because the minimum in the first row is not the maximum in the column. The minimum in the second row is not the maximum in the column, so there's no saddle point. So suppose player one chooses strategy one with probability x1 and x2. What is the payoff to player one? So x1 is the probability of choosing strategy one. So if player two chooses strategy one, the payoff to player one is as follows: 3 times x1 plus minus 1 minus x2, which is 3x1 minus 1 minus x1, because always x2 is 1 minus x1. Sum of the probabilities is 1. So this is minus 1 plus 4x1. And if player two chooses strategy two, the payoff to player one is what? It's -2 with probability x1 plus 2 with probability x2. This is -2x1 plus 2 times 1 minus x1. This is 2 minus 4x1. So we graph these two lines in the plane for x between 0 and 1. So -1 plus 4x1, this is a line with y-intercept 1 and slope 4. This is a line with y-intercept 2 and slope -4. Looks like that. So for any given strategy, the worst that player one can do is given by this red line, and you have your work as good as possible when you choose this value of x1 to be your probability. That is the intersection of these two lines. -1 plus 4x1 equals 2 minus 4x1, which is the same as 8x1 equals 3. So you choose x1, strategy 1, with probability 3/8, and x2 with probability 1 minus that, which is 5/8. So the expected payoff to player one is, just plug 3/8 into this, -1 plus 4 times 3/8, which is 12/8 minus 1, which is a half. So if player one chooses the optimum strategy, he or she will always win at least a half. Can't do worse than that. Now, let's look at this game from the point of view of player two, right? Because this is the payoff table for player one. Suppose we look at player two, and this is the second part of the homework problem. Construct the payoff table for player two. So here I'm going to put player two here, player one here. Now, from the point of view of player two, this was the original playoff table. This was player two. This was player one. So if player two picks strategy one and player one picks strategy one, player one wins 3, which means player two loses 3. If player two picks strategy one and player one picks strategy two, player one loses $1, which means player two wins $1. Similarly, if player two is picking strategy two, this is what happens to player one. So what happens to player two is the negative of each of these, 2 minus 2. So this is the payoff table for player two. And again, there's no dominating strategy. Suppose player two picks strategy one with probability y1 and strategy two with probability y2. So if player one chooses strategy one, the payoff to player two is what? So player one chooses strategy one, the payoff to player two is -3 times y1 plus 2 times y2. And again, y2 is 1 minus y1 because the sum of the probabilities is 1. This is -3y1 plus 2, 1 minus y1. This is 2 minus 5y1. So as y1 goes from 0 to 1, if player one chooses the pure strategy one, this is the expected payoff to player two. And the other choice for player one, if player one chooses strategy two, the payoff to player one is what? It's y1 minus 2y2, which is y1 minus 2, 1 minus y1, which is -2 plus 3y1. And now we graph these. This is a function of y1. We get two straight lines. This is a line with y-intercept, or 2, slope -5. And this line has y-intercept -2 and slope 3. Not a very good picture, but let's see, hopefully I did my arithmetic right. So the point of intersection is where 2 minus 5y1 equals -2 plus 3y1, which is the same as 8y1 equals 4. So y1 equals 1/2 and y2 equals 1/2. So the best strategy for player two is to choose each of her strategies with probability 1/2. And what is the expected payoff in that case? Expected payoff to player two is 2 minus 5 times y1/2, which is 1/2. That's 2 minus 5/2, which is -1/2. So this is exactly consistent with what we got when we did this problem from the point of view of player one. For player one, the expected payoff was 1/2. For player two, the expected payoff is -1/2. Well, whatever one gets, the other loses. So if player one wins 1/2, player two loses 1/2. So, and this is exactly an instance of the minimax theorem in game theory, which says if each player optimizes, chooses probabilities in these mixed strategies, so you make your maximum loss as small as possible, you come out with exactly the same result for both players. And that's exactly what happens here. Player one wins 1/2. Can't lose more than that. Player two loses 1/2. Can't do worse than that. Okay, so there'll be a few more homework problems, but this is the example, and it takes a little bit of time to understand what's going on. The text is clear, but you have to read it and think about it quite a bit. Okay, that is section 15.4. We have one more section to talk about, which is solving games when you have more than two strategies, and that goes back to integer programming, linear programming, which is good. That's it.